Hey everyone, welcome to this explainer. If you've been searching for a rock-solid blueprint to build a future-proof, high-paying career in modern engineering, you are in exactly the right place. Today, we're breaking down the specific pathways that are literally reshaping the physical and digital world.
Let me ask you something. Do you want to actually build the future? Are you ready to design smart machines, program autonomous robots, and become the driving force behind the next industrial revolution? Because if your answer is yes, then this engineering blueprint is custom built for you.
Okay, let's dive into this. Here's our roadmap for today. We'll cover the evolution of engineering, mechatronics versus robotics, what's inside the curriculum, solving real-world industry problems, some great student study tips, and finally, those salaries and the global career scope.
All right, starting right off with Section 1, the evolution of engineering.
You know, historically, engineering was kind of kept in these neat little boxes. Traditional engineering had a super single-discipline focus. Mechanical engineers dealt purely with physical moving parts. Electrical engineers handled isolated circuits, and that was that. But today, we are moving way away from those isolated systems. Emerging fields are all about concurrent engineering and cyber-physical systems. Hardware and software are now being developed at the exact same time, integrating real-time data and Industry 5.0 principles. And honestly, this massive shift has created a huge demand for the exact skill sets we're about to explore.
Moving on to Section 2, Mechatronics versus Robotics.
Let's start by breaking down mechatronics. Think of it as the ultimate foundation. It's this incredibly broad integration of mechanical engineering, electronics, control systems, and computer science. Basically, it blends sensors, actuators, and microcontrollers to create really versatile smart machines. It's the glue that binds all these different pieces together into one intelligent, automated system.
So the crucial point here is understanding the professional difference between the two. Mechatronics requires this really broad skill set focused on system integration. These are the engineers who are the backbone of manufacturing, optimizing industrial automation, and driving innovations like smart appliances and EV drivetrains. Robotics, on the other hand, that's a highly specialized subset. These engineers focus heavily on AI-driven autonomy, robotic manipulators, and machine learning path planning. To put it simply, mechatronics makes the factory smart, while robotics builds the specific machines that perceive, reason, and act entirely on their own within that factory. Let's move to Section 3 and see how this builds inside the engineering curriculum.
So, what does the actual university progression look like? Well, in Year 2, you dive headfirst into industrial automation and kinematics, really learning how to make physical mechanisms move with absolute precision. Then, by Year 3, things get really interesting. You're tackling digital twins and computational intelligence. This is exactly where you learn to advance artificial intelligence, making future factory systems instantly adapt to changing conditions. And by Year 4, you're mastering robot dynamics, control systems, and even specialized sectors like agriculture tech. You literally evolve from learning basic mechanics to mastering neural networks.
But hey, it's definitely not just reading textbooks. There's a massive hands-on lab component here. You're going to master industry-standard tools like ROS simulators, wire up actual programmable logic controllers, and use MATLAB and Fusion 360. You'll be writing code in Python and C++ and connecting sensors using industrial IoT gateways. Getting your hands dirty in these lab environments is absolutely crucial. It's the perfect foundation for grabbing those advanced robotics certifications and building the exact skills you need to shape autonomous systems.
All right, Section 4, solving real-world industry problems.
Now, what's really interesting here is how these exact skills are applied to solve massive global challenges. Let's look at healthcare. A mechatronics engineer might design the responsive physical feedback sensors of a smart prosthetic arm, while the robotics engineer writes the algorithms, giving a minimally invasive surgical arm its autonomous precision. Or look at aerospace. Mechatronics ensures a physical drone flies stably, but robotics is what programs that UAV to autonomously map out crop fields. In logistics and automotive, they team up to build autonomous mobile robots for warehouses and advanced EV drivetrains. They're tackling the exact same industries, but solving entirely different layers of the puzzle.
Which brings us to Section 5, Student Advice and Study Tips.
I absolutely love this piece of advice we found from a Reddit user. They suggest diving into Tinkercad. It's a free web simulator, and it allows you to safely test out your algorithms, build electronic circuits, and even simulate single-board computers like Arduino and Raspberry Pi before you ever touch physical hardware. It is such an awesome, encouraging way for aspiring students to just start practicing their system integration skills right from home.
And here's another absolute lifesaver. Keep a consolidated formula notebook. Because this blueprint covers so many different disciplines. You're going to be juggling math from thermodynamics, solid mechanics, electronic circuit theory, and control mathematics, literally all at the same time. Keeping a single go-to rules of thumb notebook will save you so many headaches when you're trying to balance that heavy, diverse math load, especially when you're designing those complex final year projects.
Let's wrap things up with Section 6, Salaries and Global Career Scope.
$53.64 billion. That is massive. The global robotics market is projected to cross the $53 billion mark by 2026. This kind of explosive market growth is driving a truly worldwide demand for these specific engineers, the ones who can seamlessly blend the hardware with the software.
To put this into perspective, let's look at India as a prime example. Top recruiters are offering some really premium starting packages. Mercedes-Benz India is offering around 11,40,000 rupees a year for automation and systems integration experts. Companies like TCS and Siemens are heavily recruiting too. The industry average for freshers ranges from 3 to 6 lakh rupees, and trust me, that climbs rapidly once you gain those specialized AI and autonomy skills.
And the global scope? It's just immense. Countries all over the world are offering incredible compensation for experienced talent. Over in the US, overseas salaries can reach $141,000. In Germany, which is basically the heart of Industry 4.0, you're looking at packages around 95,000 euros. And in the UAE, compensation can hit 400,000 dirhams. The worldwide need for people who truly understand both mechatronics and robotics is completely undeniable at this point.
I want to leave you with a highly encouraging final thought. The future belongs to those who build it. Whether you choose the broad, versatile path of mechatronics to integrate complex factory systems, or you take the highly specialized path of robotics to push the boundaries of artificial intelligence, you are securing a vital role in our technological future. You are the innovators who will build tomorrow.
So, here's my final question for you. Are you ready to engineer the autonomous systems that will define the very next industrial revolution? The tools are ready, the industries are definitely waiting, and the choice is completely yours. Thank you so much for joining me on this explainer today. I really hope this helps you build an incredible, high-paying career. Keep learning and keep building.